All right, in this next segment, we're going to move beyond just looking at the rates to looking at the concentrations over time, right? Up to now, we just said, okay, let's figure out what the rates are given the concentrations. But usually what we're measuring is the concentration. How can we relate the rate at any given time to the concentration at a given time? So the learning objectives for this segment are going to be calculate the amount of reactant remaining over time using integrated rate laws for several simple rate laws. We won't cover everything, but we'll cover the most important cases. First order unimolecular reactions, second order unimolecular reactions, and zeroth order reactions. And so we'll be able to, the goal is to recognize each of these rate laws from graphs of the amount remaining and calculate rate constants from half-lives and recognize the relationships between the rate laws from the units of the rates and their half-lives. All right, so digging in, let's start. So what we're interested in now is not just what the rate is at a given time, but what the concentration is at that time. So let's take a look at a first order rate law. Looks something like this, the disappearance of A as a function of T. And now we're using the differential form. Not just a delta over an arbitrary time interval, is equal to minus the rate constant times A. So that would be a standard first order rate law. Okay. So what are the physical reasons you might have a first order rate law? A reaction is occurring within a molecule with constant probability over the time. So something like radioactive decay, spontaneous decomposition on exposure to light. This will be something that only depends on the concentration of the molecule. The amount of product produced just depends on the amount of product, the amount of reactant. Okay. So here's our first order rate law. And what is this? So we want to solve for something. We want to solve for A, but A is not a value. A is a function, right? It's the concentration as a function of time. So what we have here is a differential equation, an equation for a function. Some of you guys might be covering this, some of you guys might not be, so we're not going to go and solve for what the function is. However, we can, it's a differential equation. The solution, and I encourage you to plug in to show that it is indeed a solution to this differential equation, is that the concentration of A as a function of T is equal to the initial concentration times exponential minus KT, where that K is the rate constant that occurs in the rate law. So again, plug that in and just see for yourself that it does indeed satisfy the condition that the derivative of A as a function of T is equal to minus K times the concentration of A at any given time, right? So this is true. This is true for any time. Okay. So what we get is something that looks like this. You start off with initial concentration, then it decays with an exponential decay. Never goes negative, just keeps approaching closer and closer to zero, right? You can't have negative concentration. Another interesting thing to see that can help visualize what's going on. So let's rearrange it. Let's divide both sides by A0. Then we'd get A at a function of T divided by the initial concentration is equal to an exponential. And if we take the logarithm of both sides, right, there's an exponential there. When I take a logarithm, it becomes log of this ratio. Concentration at T divided by initial concentration is equal to minus KT. And so just rearranging that a little bit more. So we have the functional dependence on one side. We have log of the concentration as a function of time is equal to minus KT plus log of A0. And that's a constant. So this is in the form y equals mx plus b, right? This is, this is going to be y equals x, right? Our t is our x here. T is our independent variable plus b. And so the slope is minus t, right? That's what we're multiplying the time by. And the y-intercept is log of A0. So you can look at an exponential graph like this, or you can plot the log of the concentration versus time and see a nice linear plot. Okay, so that's the integrated rate law for a unimolecular concentration. We go from what is the rate for any given concentration to what is the concentration as a function of time. And we're doing an integration. When you solve a differential equation, you're essentially doing integration. So let's practice this. First order kinetics, the follow reaction is first order in this cobalt complex with, it's cobalt 3 complexed with three molecules of ammonia and a bromine. And the rate constant for it falling apart is 6.3 times 10 to the minus 6 inverse seconds, a rate constant for first order reaction is going to have order inverse seconds. We give an initial concentration. What's the molarity after a reaction time of 10 hours? It's been sitting around for 10 hours. Let's dive in and do some calculations. So we want to use the integrated rate law. What's the integrated rate law? Concentration of A is equal to A0 times exponential minus KT. One thing I find a little easier to deal with is we divide both sides by A0 and take the logarithm. Then the logarithm of the ratio of A0. And now this is all personal preference. Everybody likes to do these in different ways. So we know what a minus KT is, because we're interested in time, 10 hours. So this is equal to minus 6.3 times 10 to the minus 6th inverse seconds. That's the rate, the units of the rate constant, times 10 hours. And of course, the rate constant is in seconds, so we have to convert 1 hour, 3,600 seconds. The seconds cancel, the hours cancel, and a logarithm of a ratio of concentrations, that should be a pure number, so we shouldn't see any units here, equals minus 0.2268. All right, so we have log of the ratio of concentrations equals minus 0.2268. And now we can take the exponential of both sides. We get, because the exponential of the logarithm is just whatever was in the logarithm, equals exponential minus 0.2268, which equals 0.797. We multiply by both sides by A0, and we get that A is equal, concentration of A is equal to 0.797, whatever the initial concentration was, which is just going to be, the initial concentration is 0.1 molar. So we get 0.797, that's a pure number, times 0.1 molar is equal to 0.09797, 0.0797. It's a relatively slow reaction. So it starts out at 0.1 molar, and after 10 hours has gone down to about 80% of what it was. It's 0.0797 molar. So that is the way we approach these types.